Good afternoon, everybody. I'm Tony. I started AIMSEC about 20 years ago, and before that I worked in Cambridge University. And before that, for many years, I was a school teacher.
My name is Caroline Ainsley. I'm from the UK, and I founded Bubbly Maths, which is all about taking away the mystery of maths and doing a lot of hands-on. So Tony and I have collaborated for a while now. I'm very much the hands-on person, and I've got a very strong interest in a passion about that every child on earth should love learning mathematics.
See from her picture, Caroline does wonderful shows, often with balloons and bubbles, but all about mathematics. She's very connected with Africa, aren't you, Caroline?
Very much so.
And what about you, Sam?
Thank you. Samuel Okoth Ogalo. I'm a mathematics teacher from Kenya. African Maths Initiative is a non-profit organization by mathematicians and mathematics educators that is committed to creating a stronger mathematical culture and community of mathematicians across Africa at all academic levels. African Maths Initiative is involved in projects that are aimed at enhancing maths education at all levels, from primary schools, projects called Happy Classroom, working with schools to provide learning resources and teaching aids in the teaching walls, maths clubs, maths camps, virtual maths camps, technology in education, 21st century needs in technology in education, electronic assessment system for schools, and learning resources.
Is there anything that the African Maths Initiative can offer the teachers that aren't in Kenya?
Yes. So African Maths Initiative is also working with other African countries to run maths camps. At the moment, we run the camps virtually, and we work with local and international volunteers to create resources for the camps and share the resources.
Tony has put the link on the final slide at the end. There's a link to all of these activities, and that includes the African Maths Initiative if anyone wants to contact them.
The things we'll be focusing on today and the learning activities would improve knowledge and understanding of symmetry, and that means reflections, rotations, and translations, and also systematic planning and working creatively. Systematic planning and creativity is really important. So what we have here is the learning spiral. Now, some of you have seen it before. The idea is that we're involved in, to have very rich lives and enjoyable lives, we're involved in lifelong learning. From the time we were small babies, we were learning a lot as babies, and we're still learning whatever age we are, and that makes life interesting. What you have there is the idea that in school, the children come on to this spiral and they revisit the same ideas at a slightly higher level again and again during the time they're in school. And when they reach the school leaving age, there's a platform there which launches them into the adult life, and to continue learning. So now what I've done here, rather unusually, is to provide you with a list of what we're going to do today, but starting at the lowest level, because we're thinking about how we work with very young children on ideas of symmetry, and we're going to have an activity you could do with any age group. We're going to make some symmetric patterns by folding and cutting paper, and that's where some of the creativity comes in, although there's a lot of creativity in our activities today. We're going to be creating patterns, we're going to be planning and working systematically. We're going to be identifying those transformations, reflections, rotations, and translations. We're going to be looking at combinations of reflections in intersecting mirrors and in parallel mirrors. And then at the end, we're going to be thinking a little bit and learning about how symmetry is applied in science, and right to this day, making new discoveries in science.
The more you participate, the more you will be able to learn. And also, do not fear giving any answers. Just share with us what you have. Thank you.
We say to learners quite often, if you're not sure, just make a guess. I mean, just get engaged with the ideas, and then that way, you will feel involved and you'll learn more.
Now, if you could just look at anything around you, just to begin from your hands, some of the most basic symmetry you have around you. What do you notice? Could you try looking at the mirror or try imagining if you were looking at the mirror? What would you notice? Do you have any other examples and any symmetric pattern in your body? Just look at anything that is in agreement in terms of dimensions, proportion, or arrangement. And please share with us. We have feet, palm, face, ears, eyes. Now, have a look at the two grids that are here. These are 3x3 grids. What do you notice about their symmetry? Would you say that they're symmetric or not? If they're symmetric, can you notice a mirror line? Letitia says the first one is symmetric, the second one is not. If you notice that they're symmetric, can you notice a mirror line? If they are not, can you notice why?
The one with the green squares has a mirror line. I'm not so sure about that. What about the one with the blue squares? I've put in the mirror line now.
I was wondering, Mary, if you could actually draw the mirror line with the green squares to see where it is. That's a really good way to help the young learners to actually then draw in, first look and then draw in the mirror line. And then, is it the same?
Just another quick look at this. It's got lots of examples of symmetry. You see quite a few examples in symmetry from nature there, the flower, the honeycomb, the butterfly, the cat. And you see some man-made objects like the building and at the bottom, and on the other side at the bottom, the gardens that are laid out symmetrically there on the roads, paths, and the skylight. Now, the skylight's got circular symmetry, as has the pink pattern in the middle and the flower, whereas quite a lot of the others have got reflection symmetry, which we've just been looking at. Now, with the elephant there, you can see his reflection in water, and often water acts like a mirror. And on the right, you see that mountain. That's called Mirror Lake, and it is really so calm that you've almost got a perfect mirror image there. And a few more examples there, and including Leonardo da Vinci, who was, as well as being a great artist, he was a great mathematician and scientist. And very curiously, he always wrote back to front in his notebooks, that reflected writing like.
We've got a comment, the cat and the butterfly have some wonderful symmetry. And also going back to the mirror, the lake mirror, if you find a picture and turn it upside down and present it to your learners and ask them which is the if you get a really good one, which is the actual sky and mountain and which is the lake image, that can be an interesting exercise. This one is reflection symmetry, and so we're just looking at where the lines of symmetry are, and remember also, for example, with the picture with the prisms on it, with the black plane, you can see the plane there, and so it's not just, we've got the lines of symmetry if we just look at the faces of the prisms, but we also have a plane of symmetry underneath the prisms, so you have like the full 3D reflection as well.
Unlike those prisms, we're not actually perfectly symmetrical, and with some software you can very quickly cut your face, picture of yourself, cut your face in half or use somebody else's face, and then reflect it and make your face again with the two halves of your face, which are actually the right-hand side and its reflection, and you'll find you look quite different. So we are almost symmetrical, but not perfectly symmetrical, which is quite, I think, quite interesting. Now, if you want to be creative, Caroline, you can get some paper.
I do, yes, I've got my paper, and this is, I'm actually using square paper, because then not only can you, and this can be done by really young learners, the age doesn't really matter, and you can do whatever shape. If the child likes dinosaurs, then whatever shape they want. But start off, and I certainly did this when I was a child, start off with just a doll or a person, because that's whatever the children are interested in, and take the legs down. It can be rough. This is rather rough, and we've got two legs, so go back up to the legs and then open it out, and you've got a perfect demonstration of symmetry, because you can just do that without the scissors, and then I've also got the option to do it with scissors. But the thing I liked about this is you've got the squares there, so you can actually really see the symmetry, and that's just a great activity. And then you've got the snow. I love doing the snowflakes. I remember I did that when I was a child. I used to decorate. Whenever there was a party, my mum and I would make snowflakes, and you just literally fold. What do I do? My scissors. Fold a piece of paper. I'm just going to cut it. I'm optimizing my usage of paper. So you take a piece of paper, fold it in 4, and then make sure you don't cut it off completely. You can just do straight lines and use child-friendly scissors. Just cut. I'm just doing triangles here. You can do a little square here. You can do round shapes. Not a square, obviously, a rectangle. You can do maybe a round shape there. And a nice place to do, well, we've got it there. Now we've cut just one line in the corner there where all 4 sheets of paper came together. So this is a great time to say, what shape is that going to be when we open it up, and visualize what shape are these going to be when you open them up. I could do a lot more shapes than this. And you can also put a shape right in the middle as well, in the center there. And what shape is that going to be when you open it up? And then when you open it, it reveals the symmetry, but it also reveals some surprises about what the shapes have become.
And Caroline folded it in 4, making 2 folds to fold it in 4. But of course, if you want, you can make more folds, and then you get a different, slightly different pattern. But we leave that to you to experiment with, and I'm sure your learners will learn a lot about geometry, a lot about shape and reflections, and they'll do it and have fun and not realize they're learning.
Now we have looked at reflection, and we have looked at how we can create a perfect symmetry from reflection. Now let us look at rotation symmetry. Rotation, just from definition, a rotation is the turning of a shape about a fixed point. Now imagine a shape. We can consider a shape to be having a rotational symmetry when it looks the same way, or it looks the same after some rotation that is less than 1 full turn. So if you try rotating a particular shape, for example, we have a few shapes presented here. Now, after less than 1 full turn, if the shape looks the same, then we could say that the shape has a rotational symmetry. Now, in this activity, we are going to pick any shape and try to look if the shape has a rotational symmetry, try to see the number of orders. First, we are going to determine if it has a rotational symmetry. We try to find the order, and then we go ahead to find the angle of rotation. So say, for example, we have a yellow star. that is already been presented here that has order 10 and angle 36. So how do you determine the order? We'll say the order is how many times that the shape matches the pattern, or if it looks the same as you go around about a fixed position, then we could use that to count the number of orders. So that way we can determine that the shape that is described there as order 10 and angle of 36. The beautiful shapes that are created here are from basket weaving. There is an interesting mathematical pattern in here. Just look closely and pick any and describe. If it is symmetric, you can describe by giving the order. If they are symmetric, you can describe the order, the angle of rotation, and you can also let us know if any shape exists here that is not symmetric.
And you might have something at home that is similar as well. Identify things that are similar that have rotational symmetry at home.
So all of these baskets have got rotational symmetry. You need to count. Some of them are more difficult to see than others, but what you need to do is to just count the points of the stars.
So Mary says she has picked the purple-white flower, symmetrical, order 12.
Order rotation of 2 for you're talking about the mural, I think, Mary, if I'm correct.
Order 2. Yes, she's saying order 2. Yes.
And that's something your learners can make posters of on the walls of the classroom or at home, and some beautiful art and examine symmetry at the same time.
Continue putting there while I also pose another challenge here. What do you think? Just have a look at this and while you're trying to describe them, do you think there's an order 1 rotational symmetry? Do you think there exists an order 1 rotational symmetry?
That's a sneaky question, Samuel.
Well, Mary says there is no order 1.
I can see.
Anyone with an answer?
I can see. I mean, even the dolls have order 1. You just rotate them 360 degrees, right? Have I got that right, or am I barking up the wrong tree here?
Well, Sam said that you had rotational symmetry if there was an angle less than 360, about which you could turn it, turn the object, and it would still look the same. So if you take that literally, then there would be no order 1. But actually, you could say everything that's not symmetrical has order 1.
That's what Mary says. There's no order 1, but in other words, if it's order 1, it's not symmetrical. So yeah, that's what I was thinking. Everything has order 1, because you just literally do a loop the loop with it, turn it around and put it back where you found it. And it's.
But looking at these baskets, which are a lovely example of African art, so much of art and craft involves mathematics in some way, insofar as the designer or the artist had to plan the pattern as they made it, and that involved getting the angles right. So when the article's finished, you can see the symmetry. So in lots of artwork and in design, not just the basket work, beadwork, murals, design in fabrics, so many places we see symmetry, which just doesn't happen by accident. Somebody has been thinking mathematically, even if they didn't call it that. Somebody doing knitting or crochet work is often, without perhaps recognizing it themselves, doing mathematics. And there's something else I want to say, and that is, this is part of a culture. A lot of artwork is part of a culture. And very often the youngest people in the society, very much more involved with the modern culture of screens and not the best necessarily of Western culture, and maybe don't know a lot about their own culture. So it's really a good idea to use your local arts and crafts as a basis for teaching the geometry sometimes. Now we're going to move on to looking at the big challenge which this is all built around, and that is, can you take 9 squares, and that we've made lots of copies there, so to suggest that there's lots of ways of answering this question. Can you take a grid with 9 squares and just shade some of the squares to make symmetric patterns? And how many ways can you do that? How many symmetric patterns can you find? And you see the green one there is symmetric, and it's got, they're marked 4 lines of symmetry. So you can reflect it in horizontally, vertically, and in either of the diagonal lines. It's also got rotational symmetry. So it's got all the symmetries you could possibly imagine there for this sort of rectangular sort of square pattern. Now in contrast, the yellow pattern has just got 1 line of symmetry. So what we want you to do is to quickly draw your own grids and start shading some patterns. And how many can you find?
If you have square paper, then you just use square paper. It's really easy. I'm using my whiteboard here, so I'm just going to think of one that has symmetry and color it in. I'm going to choose a super simple one. There you go. Whoops, I've colored my one in there. So I've just drawn them big on here, but you can just use a bit of square paper and just go ahead and see how many you can find. And pretend you are a young learner and see what you'd find as a young learner.
So Caroline has actually shaded just 1 square there. Now, she could shade 2 squares. And there she's got another symmetric pattern. Or she might choose to shade 3 or 4 or 5 or 6 or 7 or 8 or all 9 squares. So you can see there's lots of possibilities. Now she's doing 3 squares. But what about you? Why don't you have a go yourself and make some patterns that are different from Caroline's? Okay, she's shown you 1, 2, and 3 squares there. And if you've got other people with you, then look at each other's patterns and put, pool your pool your answers. How many can you make all together? I'm not sure. Dicker Lady says that the second one is not symmetrical. If you put the second one, Caroline's drawing in the line of reflection there. It has reflection symmetry.
You're quite right. It doesn't have horizontal line, unless I could turn it that way. I'm revealing a little bit of what we're between later. But the lovely thing about this is that you can get all the learners to do the activity and then identify which ones, like if you've got copies, if they've both done the same thing, then you pull it together and so they're looking for something that no one else has done. That's a very powerful exercise.
So that what we're trying to say, we haven't been very clear about the actual task here, insofar as what does symmetry mean. But we're just exploring symmetry now, and let's try and be clear about what we mean. If there's a mirror line anywhere, then we're calling that a symmetric pattern. There can be 1, 2, 3, or 4 mirror lines. Okay. And if it's got rotational symmetry, like the baskets that we saw just now, then it has a different sort of symmetry. And when we're talking about rotational symmetry, we need to say where the center of that symmetry is, where it's being rotated about. And in the first pattern that Caroline's drawn, the center of symmetry is right in the very center of that one square. It's quite a rough drawing, so she's not put her lines in exactly. If you look,
no, I haven't. Yeah, but I'm going to draw the dot in now because I can't see it.
There you go. There you go. So all the lines of symmetry go through that center of rotational symmetry.
And then this one. Now this one, you're quite right. This has an order of symmetry, of rotational symmetry of 1. We're back to that again, Sam's idea. We could maybe make another one here that does have rotational symmetry, as well as it's got horizontal, vertical, diagonal, and rotational symmetry for this one.
But we're saying it's symmetric if it's got any sort of symmetry, and it might have reflection symmetry and not rotational. So
like this one. This one has only reflection. It doesn't have rotational symmetry.
Now we're moving to lower secondary. So at the primary stage, it was largely exploratory. We wouldn't be insisting that they identify patterns as the same. We'd just be letting the young learners explore these ideas of symmetry.
Let us move to the next challenge of symmetry. Just like Caroline has demonstrated to us, can you try shading any grid? You can try to shade one grid at a time, or 2, or 3, and so on. Are you able to notice that while you look at the grids, say, for example, if we choose to paint 3 grids at a time, like shown in the yellow shaded patterns, you realize that we have 4 different patterns. The 4 different patterns can only be counted as one because they are under one rotation. If you have a closer look, you'll realize that they are under one set with 4 different patterns. So we will count that as only one pattern. So using this, can you try, for example, shade to create similar patterns? Let us begin by picking only one grid at a time. So say, for example, we want to shade the grid at the top left. When we try shading grid at the top right and at the bottom right and at the bottom left, we will have the same pattern under one rotation. So we will have 4 different patterns under one rotation, and we will consider that under one set. And so that only one of that will be counted.
We're trying to reduce the task because actually there are more than 60 solutions here, and we want to find them all. But to make the task easier, we're going to group the solutions together so that, and we're going to actually have to be quite clear about what we mean by different. So we're going to call the yellow designs on the screen there, we're going to call them the same because they're all rotations of each other. So we'll only need to record on our solutions 1, and it will represent all of them. You've done this with number, for example, because when you record the number 3/4, the fraction 3/4, you need to teach the children that if they have 9/12 or 15/20, and there's lots more fractions that are equivalent to 3/4. You've got what you call equivalent fractions there. Now here we've got equivalent patterns. So we see a set there on yellow patterns that are all the same. They're counted as one pattern. And that's repeated 4 times, but in other sets, they're just repeated twice. It's all about working systematically. If we move on now to the next slide, it's about key questions, which we think are very important, don't we, Caroline?
Key questions are one of the most powerful things. I knew about key questions. I knew about great questions before I met Tony, but Tony is the queen of the key questions. And it's all about helping the learners work it out for themselves by not telling them, not explaining, but by asking them questions whereby they can disentangle, where they can figure it out for themselves. And that is the most powerful way to learn. And you've got 13 key questions right here that are literally given to you. And there's lots, if you use the Aiming High resources and activities, every single Aiming High activity has key questions in it. And when you're transferring to different area, you just can use the same question, like, are there any more symmetric patterns with the same number of squares shaded? We can change that to, are there any more fractions that are equivalent to each other? You can, there's so much power in key questions, and it is something you have to train yourself to do, because we're, myself included, in the habit of, from being young, of just explaining, and if someone asks you a question, you want to help them, you want to give them the answer. The answer is actually to ask a question. And the same goes for the parents. You can get the parents to always ask a question instead of giving an answer.
Yes, and some of those questions are very general. How will you record your findings? How will you write them down? It might be, you might be writing something, or you might be drawing a diagram. That would apply to lots of different mathematics. Sometimes you have to be rather precise about what you mean by the question. I mean, number 3, which patterns are the same and which are different? We've just discovered that the patterns that look different, we're actually calling them the same because they're rotations of each other. So we have to be very clear about that. But it doesn't matter if the first thoughts are a little bit fuzzy, because it's in making the meaning clear that you've got the learning. And learning is should be all about understanding, about making meaning. Really, not just knowing how to do something because that's a habit that you've been taught, but knowing how to do it because you understand it. And it makes it much easier for children to remember things if they understand them. Instead of doing your explaining, as Caroline's just said, ask questions and listen to what the children say about the answers.
I was doing that on the sheet I was doing, that they don't have to draw every single patterns.
Instead of drawing 120 or 30 or more patterns, we're just going to draw 60. They're not the same. What Caroline is showing you is what would quite possibly be the work that you'd see a learner do. And this idea of what we mean when we use the word same and what we mean by using the word different is going to be to emerge as you work on this. So we have said that rotating the yellow pattern that you see at the top right-hand corner there and its other 3 images, we're going to take them as being in the same set. But we're not actually going to say that those 2 green patterns you see below, one with 4 shaded green little squares and one with 5 shaded green little squares, we're not going to say they're the same, because what we're going to do is to find more than 30 different patterns, and then we're going to say to each pattern there's a complementary pattern. So that's a word that occurs in other places in mathematics, that word complementary. It means the 2 are different from each other, but in some sense they belong in a pair. It should be clear that whether you've got 4 squares or 5, they're complements of each other. And then you can see that with the yellow shading there. The 3 yellow squares are shaded in one of those pictures and 6 yellow squares in the other picture.
You can show them a real life example of this. If you can find the filter on your phone, you turn pictures into black and white. And then if you find a negative filter that then turns everything that's white into black and everything that's black into white, you can actually demonstrate this using modern technology. In the olden days, it would be called a negative, but these days you can use filters on your phone, photographic filters.
So what we're going to suggest then is that all the work needs to be done is going to be shading either no squares 1, 2, 3 or 4, because the 4 squares are going to be complementary to 5, so we won't bother shading 5. 3 squares are complementary to 6, and the 2 squares are complementary to 7, and the 1 squares are complementary to 8. So we're only going to be shading 1, 2, 3 or 4 squares. Now, looking at this, what we've got here is some way of organizing the results systematically. So after your class and your learners have worked on it, and certainly this should be the challenge for upper secondary, can they find them all and can they prove and explain the system so that everybody's sure that they found all the patterns. So what you see here is that up at the top you've got 0 and 9 shaded squares. There's only one way you can do that. And then you can have 1 or 8 shaded squares, and there are 3 ways for that. Now the number of grids there doesn't correspond to the number of solutions in the other boxes, but what we have said is that 2 shaded squares is complementary to 7, 3 shaded squares is complementary to 6, and 4 shaded squares is complementary to 5. So we're only going to have to complete this grid with 0, 1, 2, 3 or 4 shaded squares and find them all, and then we'll have got all the possibilities. If you want to, you can work on this plan now. I've given you a systematic plan. You can work on it to see if you can find all the patterns. And another way to do this systematically is to use color coding. So I've used green when it's been 4 squares, yellow when it's been 3 squares, and if you like to use different colors for 1 or 2 or 3 or 4 square, little squares shaded, then that's another way of having a system where you can show people how many there are of each type. Now, rotations and reflections of the same shape are put into one little package, one little set, or equivalence class by them, all together. And we're only doing this because it actually cuts down what we show as the solution, cuts it down to the bare bones and makes it very clear. If we have 100 we might have hundreds and hundreds of these if we did all the repetitions. So we're actually going to cut it down, and we'll end up with just 64 solutions, but we'll only shade 32 of them because we've shown that the solutions come in complementary pairs. Okay, so we're going to show 32, that's what you're aiming for, and we're going to say yes, and to each one of those there's a complementary pattern with, as we explained, and so altogether there are 64 solutions. Now I wanted, while you're thinking and shading more of these, I wanted to just mention how valuable a task like this is in the classroom, because it's so motivating for children, and very often it's the ones who are not top of the class and getting everything right first time who can excel at something like this. First of all, because it involves a different sort of skill. It involves being able to visualize patterns and having some sort of artistic skill, rather than just being very good at numbers or other mathematics. But more than that, their perseverance will be rewarded. So some people who do quite well anyway, maybe they get away with getting the right answer too easily. And what we're going to say here is, if the challenge is there, we've only found 25, that's not enough. There are more. Can anybody find another one? And then the next day or a few days later, somebody in the class can come up with one that nobody's seen before. And then that person is the star of the moment. That young person should be congratulated and praised for finding one that nobody else has found. So what I like to do with a task like this is to put the chart on the wall and to say to the children, well, we haven't found them all, but that's fine. We'll go on looking and see if you can find another one, and come and tell us all. And then when a student comes with one that they think is new, get the whole class involved with looking to see and checking if it really is different and a new one, and if it is, put it on the wall in the poster. And you can even put the name of the person who discovered it in your class by that design. So it's very good for getting the class engaged in teamwork, where everybody contributes to the enterprise. Everybody's involved and doing what they can to make a contribution.
Write down your answers no matter what, because like myself, if there's something that you've forgotten or lost track of or don't quite understand, the best way to unscramble it is by doing it and finding out what doesn't work in order to work out what does work.
But what is so important is that nobody in your class is afraid of giving an answer in case they make a mistake, and that nobody in your class laughs or makes a rude remark if somebody makes a mistake. Okay? Mistakes are good in learning mathematics, not bad. And why are they good? They're good because they provide you with a way of thinking which then leads you to better understanding. They help with the learning. As Caroline just said, they're learning experiences, okay? So very often just don't say whether something's right or wrong, like I didn't say that to Caroline. Just let them go on, and they'll discover their own mistake probably, and they'll learn from that.
That's exactly what happened. I was like, there's something wrong here. I know there's something wrong here. Tony didn't say words. It wouldn't let me go. And I kept going back to it until I realized, I'd put in all possible patterns rather than only the symmetrical ones. So it worked. Technique worked.
So Sam, you were going to explain why these are all the solutions that exist.
And Tony, can you share the screen, please? Because we turned off the spotlight.
Oh, did we stop sharing?
Yes, at the moment, I think so.
Okay.
Thank you, and welcome back after the break. I hope you've had a good time in your break to go through shading the patterns and trying to look for possible solutions. Now, let us go through the solutions together. Try to have a look at the solutions. And just one by one. Do you realize any of the solutions that you missed when you were trying, or any of the solutions that you came up with that is not shown in the screen? And just share with us how unique have you tried to solve this, and how have you tried to come up with the set of solutions? Have you come up with all the 64 solutions in total, or have you come up with 32 complementary solutions
Or have you done like me? You've come up with solutions that aren't actually solutions, so you need to cross those out.
Yeah, yeah. And what would you do if you have unique solutions that others do not have? For example, in your class with your students, what would you do? How would you encourage your students to find their own styles or their own systems for the search of the patterns? For example, in our case here, you realize that one grid shaded boxes are having blue color, two grid shaded boxes are having a red color, and so on and so forth. So would you adopt the same kind of way of coming up with solutions? And what will you do? Say, for example, if you have students who identify or who come up with solutions that others have not come up with, whether they are right or wrong, how would you categorize this, or how would you approach this? Like Tony had said before, having the students stake up or just stake up their solutions in the board, and then getting to identify whether they are the right solutions or not. If they have unique solutions, if they are right, they will always be there. If they are wrong, they are going to provide them with a good learning experience to learn from the mistakes and know how to identify this. Which patterns did you miss here? What was your method of finding out the solutions? How would you go about this? How would you encourage your students to come up with their own systems of searching for the solutions?
But there's something else here as well, isn't there? The fact that what I put on this slide is all 32 solutions, but and then there are 32 complementary solutions, making 64 altogether. But you might have shaded one in the same set which doesn't look the same as mine because it's been rotated. So because we've got sets of 4, sets of 2, which we're putting together and we're only showing you one representative, you might have shown a different representative. So you've got to, if you're going to compare your solutions with the ones you see on the screen now, you need to look at mine and yours together and say, oh yes, but they belong in the same set of equivalent patterns. So yeah, it's a little bit complicated, isn't it? And what I like about this whole challenge is that it's something that you can do with very young learners, and then you don't actually insist that they find them all. You just pleased, and you celebrate each one, and you don't even try and say that, oh yes, these belong in the same equivalent set. It's just another pattern. You just make patterns very freely with very young children. And then you work your way through, as we have in this workshop, to the state we're at now, where together we've appreciated what's required when you want to do something systematically, when you want to represent your solutions in a way to communicate the ideas to other people, and when you want to do something that in fact summarizes in a way, in a systematic way, because as I say, there will be hundreds of different patterns if you were to separate them all out and count all the representations of the pattern after it's been rotated or reflected. But if you're going to put them into, just like with fractions, if you're going to put them into equivalent sets of equivalent patterns, then you've got to be systematic. And that is, you're only going to ask the older learners to do that in upper secondary. So this is a suitable challenge for any age group. That's really why I like it so much.
Working systematically is hugely important for mathematics, but this is about why working systematically is important in life. Many of the skills you learn in mathematics, in the mathematics classroom, even if you never use them again specifically in your life about the actual maths, the skills that you learn, you will use in life constantly. Tony likes to use the example of packing a suitcase. If you're going on a journey, you've got to make sure you've got everything that you need, or you're going to end up at the other end with something you're missing, or running back to the house because you forgot something that you can't do without. And it has also been systematic in a factory. The only way to be profitable in a factory is that everything is done systematically. Otherwise, you have complete chaos, and the company will lose money and end up having to close down and firing everybody unless they get systems in to work. The same with accounting. Teachers, you have to be systematic in terms of planning your lessons, make sure everything's done on time. Working systematically is absolutely essential.
The school timetable is an example of a system, isn't it? I mean, everybody knows where they've got to be at any given time in the school day, and what subject, and therefore what books they need, and who's going to be teaching them, because there's a school timetable, and that is a system. And there would be chaos in the school if it wasn't properly planned. But what is important about school is not the maths that it's just about getting answers and ticks and being able to do procedures. Years ago that might have been important, but those sort of routine tasks can be done by machines now. So what's really important is that as well as understanding the maths, children are learning in the maths classrooms. Great place to learn all these life skills, and one of them is working systematically.
It's a great, whenever you get asked, especially by the younger teenagers, why am I doing this? I'm never going to use this in life. It's never going to be used again. The answer is that you are learning life skills. You are learning even being courage, even the courage to speak up when you're not sure of an answer, or as basic as that. Lots being systematic, and there's reams of skills that you're learning when you're doing mathematics that will help you in life. Risk assessment, taking risks, and assessing, making decision making, lots of things.
Other things are teamwork and being able to work cooperatively. There's lots of important skills that children learn in the maths classroom. So what about this slide now? Reflections in intersecting mirrors.
Have a look at the images below. You remember this image from the weaving, the slide that we had looked at earlier on. Like we said before, that a complete or a rotational symmetry presents a repeat or a repeat of the same pattern after a move about a specific point, a move that is not less than 1. So in the examples below, this presents a different kind of view. Have a look at the first image, the second, and to the third. If you notice carefully, or while you notice, you have a look at the images, what do you notice about the combination of two reflections, vertical reflection and horizontal reflection? What do you notice? The diagrams show the design, and the designs are reflected at specific angles. What do you notice when you move from the first to the second?
The first is a reflection in a horizontal mirror, and you see the image after reflection in the middle, and then you reflect in a vertical mirror, and you see the image after that reflection on the right. And if you combine the two reflections and go from the image 1 to the image 3, Sam's asking, what do you see? So can you study image 1 and image 3 and the little piece that's sort of torn off the corner, and do you notice anything about image 1 and image 3? It's a bit of a surprising result because we've got two reflections here and they're combined.
What do you notice? Just what do you notice?
Letitia says image 3 is the upside down copy of image 1.
Well, I'm not sure what Letitia means by upside down. You see, upside down can mean a reflection, but image 2 is the upside down copy of image 1 because it's by reflection. Image 1 and 3 are not the same, though they look the same.
What have you had to do? If you just had a piece of paper, what would you have to do?
The little corner
from 1 to
is
3.
Yes, the little corner is torn off on the bottom right on image 1 and on the top left of image 2. What does that suggest to you? Image 1 and image 3, they're rotations by 180 degrees. So if you turn that design around 180 degrees with a center of rotation at the center of the little picture, you get image 1. Images 1 and 3 are rotations by 180 degrees of each other. Reflections in two mirrors intersecting at 90 degrees give a rotation of 180 degrees. So that leads us into kaleidoscopes. And in a minute, Caroline's going to show you her kaleidoscope. She's just getting it ready. So what we have here is a toy, if you like, invented by Sir David Brewster long ago, and a very popular toy, but he was a serious scientist and he was involved in studying optical mineralogy, photoelasticity, all sorts of things to do with light. And the word kaleidoscope is from the Greek. It means beautiful shapes to look at. Caroline is going to show you her kaleidoscope, which is very simple. And there you see it looks like a pattern, but actually
We've got paper with a detailed design, and what I've got is a mirror in my hand.
Caroline, now it's looking kaleidoscopic.
Yeah, you mentioned the kaleidoscope earlier. Let's see, what have we got? We've got 1, 2, well, we've kind of got 4 squares again, haven't we? And
This is amazing. Yes, 4 squares. Now, Caroline's changing the angle between the mirrors, and look what you're seeing. You're seeing more copies of the same pattern now, and multiple reflections, but all around them, not just in a long line. And as Caroline now, she has got reflections of that. Is that?
There's 6 there.
6 reflections. And so she's got her angle of 60 degrees, which means she's got 6 reflections. And now, well, you could get 8 reflections, Caroline. It's 45 for 8.
That is.
Yes, that looks it. Yes. So she's got 8 reflections now, and that's with her mirror at 45 degrees. 8 times 45 is 360.
Yes. And now.
And she's getting more and more. How many have you got now, Caroline? Oh.
I should have, in theory, this is 22.5-ish.
So that should be 16.
My mirror's a little bit bent. I don't have, the join isn't exact, but you can see those straight lines. It's not perfect, but you get the idea. And a child can be looking through here and really, really see and take pictures with a camera. And actually, it looks better with the camera than it does looking at it direct. You are getting a better view with the camera than I am getting by looking directly at it.
It's beautiful. It's a great demonstration. But how exciting this would be for children at home playing around, and all you need is some simple props, a couple of mirrors and these you know, very, very simple ways of sort of moving them at different angles. And the children will learn so much about angles and about reflections. And in the school maths, we do learn about reflections and rotations and translations, which we'll talk about a bit more.
This is the real Father Christmas right here. And you can see he's looking at the mirror behind. But if you look behind him, you can see the back of his head. And then behind that, if you can just about see that, you can see his eyes. So he's facing himself for the first one. And then again, and it actually goes on forever, just limited by the quality of the mirrors.
You can see lots of mirrors, Caroline, but you've only got 2 mirrors in this display, haven't you?
Now I'm going to show you the setup. So there's the setup. I've got one mirror here. I've got my little Santa Claus. It could be anything. I've got another mirror here. And I've just used a cardboard box. Just test with lots of different things, and all you need is a cardboard box and 2 mirrors.
What we're trying to do is to show you the results when you combine reflections. And if you combine them into intersecting mirrors, you get a kaleidoscope pattern. And we're going to show you some now. And if you combine them in parallel mirrors, like Caroline's little man, you get something different. So here, there's a question. What do you notice about these pictures? They are kaleidoscope patterns. And I promise you that they're made with 2 mirrors, and the pattern that you see is repeated many times with rotational symmetry, but it's repeated as it's viewed in 2 mirrors at an angle with each other, as Caroline just showed you. Describe the symmetric patterns, what orders of symmetry do they have, and give the angles between the mirror lines.
In Caroline's presentation, you must have noticed that while he tried to change the angle of the mirrors, the patterns were being created, the symmetric patterns were being created with different orders of symmetry. And while he changed the angle of the between the mirror lines, there was different orders of symmetry. So it is the same way 3 of these images have been created. Just have a look closely. So what do you notice? Like how many times does the same pattern matches, or how many times does it look like the same pattern goes around about the fixed point or about the center?
I think it's enough to show that the middle one's obviously 6. You have to look a bit more closely to count the number of repeats in the other patterns.
Have a look at the image here. There's a reflection in parallel mirrors, just like Caroline has shown us with the little man. Now, in this image here, there is a girl taking a picture. Now, if you look closely, do you think you can count the number of reflections that are here?
You keep coming up with those sneaky questions.
That's not easy.
Yeah, and if you can count, how can you? How many? What is the number of the reflections? They're infinite. Yeah. What do you notice about the girl taking a picture?
So look at alternate images of that girl, and
remember my little man with the opposite mirrors.
Yes. So I want to talk about the Hall of Mirrors at Versailles. So this was the King of France who'd seen these reflecting many, infinitely many reflections, and he built this Hall of Versailles with parallel mirrors, and on the left you just see one reflection, and on the right many. So you see that chandelier? Well, it's reflected set of 3 chandeliers are reflected many times. You can see from the ceiling too, lots and lots of reflections in that famous Hall of Mirrors. Here's another picture. Caroline at a museum in Spain And you'll see Caroline between some mirrors and lots of images there.
Have a look at this and have a look at the reflection of the image that is at the middle of mirror 1 and mirror 2. There is a flag. So the mirrors are parallel. What do you think about what is going to come up? What do you notice about the combination of the reflection between the mirrors? If we try to draw the reflection of the flag in mirror 1 and get the image. Now, once we have gotten the image of the reflection of the flag in mirror 1, can we try to reflect it in mirror 2? And where do you think the image will be?
That's a reflection in mirror 1, and then what you do is another reflection of the reflection of the reflection in mirror 2. So what you get is this. This one, the flag is leaning over, but otherwise it's the same. Image B1 is reflected in mirror 1 to give you B2, and then image B2 is reflected in mirror 2 this time, same distance on each side, to give you B3. And if you look at B1 and B3, you see that the two images, B1 and B3, are what we call a translation from B1 to B3, which means it's just slid across a certain distance. And the distance is actually double the distance between the mirror lines if you measure it.
And Jeanette's using east and west to help people orientate themselves which way it's pointing.
What a good idea. And the opposite ones point in opposite directions. So there you have a combination of two reflections in parallel mirrors.
Dicoletti mentioned that they change in size. They appear to change in size because you appear to be further away, but the actual reflections themselves don't change in size, as far as I understand it, but they look as though they have to you because they are optically a long way from you. So it's perspective, just like anything else, but the actual image is the same size.
Now, if you do the reflections in the two mirrors, same two mirrors, but do it in the other order, in other words, if you reflect first in mirror 2 and then in mirror 1, something rather odd happens. You get a translation from R1 to R3. What you're looking at now is the red flags. But this time the translation is not from west to east, if you like, or from left to right. It's from right to left. From R1 to R3, the translation is in the opposite direction. So by reversing the order in which you do these reflections, it goes in opposite directions. Isn't that marvellous? There's quite a lot in there. What we have seen with the intersecting mirrors is that we got the kaleidoscope pattern round in a circular pattern. And what we're seeing with the parallel mirrors is that we've got repeating patterns repeating again and again and again. And if you look at it directly, the views that we got of Caroline and of the girl we thought it was a lift, by the way, that picture. As you said, they appear to be smaller, further, because they're further away. It's like perspective.
And you can actually see this with the man with the two parallel mirrors. I was only showing you the image going one way, but because there were parallel mirrors, the learners will be able to look in and see that the images go in both directions and that the little man keeps changing direction, keeps changing the way he faces.
And your learners would absolutely love it if you got a box and two mirrors and something that you can put in the middle that will produce the reflections, if you allow them to actually move the mirrors and see what happens. Okay, so two reflections in intersecting mirrors give you a rotation, and two reflections in parallel mirrors give you a translation, which is a moving sideways. So now we're moving on to a science, sort of an advanced study now. And here we're talking about crystallography. So mathematics provides the language we need to describe the symmetries of atoms and molecules and crystals. It explains exactly what symmetries enable a unit cell to pack neatly and repetitively to make a three-dimensional crystal. In the pictures there, we don't need to understand them in detail, but if we look at them, we can see that the red rings are indicating rotation, and that the atoms and molecules have rotational symmetry in the direction shown about those lines in that picture. And on the right, you see those blue planes of symmetry where you've got reflection. Now, you might like to look at this link, plus.maths.org, because it's a magazine for older school students, 16 to 18-year-olds, and for adults. And it's about mathematics, but it's explaining mathematics in the simplest terms, and quite advanced mathematics sometimes, how it's used in the real world, in the working world, in science and in research, and what new discoveries, explaining how the maths is used in making these new discoveries. So the link there, Shattering Crystal Symmetries, is where I took those pictures, and you might enjoy it, that magazine, if you go to plus.maths.org. Okay, now here we're moving from chemistry and crystallography to particle physics. And in 1964, long ago, Peter Higgs discovered, just using mathematics, nothing else, a new particle. And he explained it in terms of symmetry groups. He knew a lot of physics, and particle physics used the mathematics of symmetry groups. And the scientific world were, they weren't altogether convinced. They said, well, it's just mathematics. Maybe it doesn't exist at all. Maybe just the mathematics is telling us a story. But then in 2012, many years later, what happened? Well, at CERN, which is a research, I'll show you a bit more about it in a minute, where they do research in particle physics, research station in Switzerland actually, they actually discovered the very particle that Peter Higgs had predicted, and the mathematics had been telling the truth, and this particle really, they could actually look at it and see it. So that shows you the power of mathematics, and for that the two scientists who collaborated got a Nobel Prize. Now this next one is an even more recent discovery.
Well, but it's I was actually in Switzerland on top of the Large Hadron Collider when it was announced in 2012, and a nice thing about CERN is that, by the way, that most of the Large Hadron Collider is not under the ground of Switzerland at all. It's in France because of the sheer size of it.
In two countries.
Oh, yeah, very definitely. There's far more of it is in France, and to actually visualize it and see it and just visualize it on a map to see where is the center of it and how big is it on a map. That's a nice activity to do in of itself, real life maths. And yeah, so since they proved the Higgs boson theory, they have since found they've improved, they've developed further the collider, this massive, great, big, huge tube that uses basically it's a particle accelerator, makes the particles to go super fast, and then they collide with each other, and that's when these subatomic particles happen. And they've discovered a number of them. It mentions one, it's a particle that has 3 quarks. So you want to start getting into the real detail, that's a great place to read up about. And yeah, this is applications of symmetry groups in particle physics. So how is this used in real life? Right here in very exciting modern discoveries.
Yes, and so maths is used in pretty much everywhere. And if children ask you what's the use of it, well, it's part of general knowledge in a sense, understanding these things can happen even if you're not personally involved in them. But Caroline had this wonderful involvement because she was staying with her sister, actually there on the spot when this discovery was made.
My sister used to work at CERN, which is why she lives there. She doesn't work there anymore. But yeah, it was fantastic to think I'm standing above where this Higgs boson particle was actually produced. Proved that the mathematician was right.
Yes. Okay, so now I want to just share with you these links. And there you'll see not just the two challenges, the two activities that we have worked on today, Symmetry Challenge and Paper Dolls, on the Aiming High website. There's hundreds and hundreds of similar activities on the Aiming High website, and activities for primary and secondary learners. Tangram pattern, mirror, mirror, reflecting squarely, the transformations and art, and flower of life are all there, and they will extend ideas, as the ideas that we've been talking about this afternoon. I like the two little pictures there, particularly the one on the right, where you'll see some learners who've made an octahedron there with paper sticks, which is for another day. Now, I also wanted to mention some links for you because I don't want you to miss your opportunity. If you don't know it already, go to Aiming High and you'll find hundreds of examples of activities like you've seen today. It's 0 rated in South Africa, so it's not going to cost you anything to use the internet when you go to Aiming High. I'm not sure about other countries, but you can also download, that's true of South Africa, but you can download, go to the app, there you have the link, and you can download the resources, use them offline. Again, that's going to be no cost to yourselves. We also have not just this sort of workshop, but we have guides for you to run your own workshops, which suggests, the guides suggest lots of activities there that you might like to do with a group of other teachers that you know, either from your own school or from your neighbourhood. So there's the AIMSEC website. I'm Tony Beard, and there's my email if you want to contact Caroline or myself or Sam. There you have the emails. And also, AMI there, we've given you the link for AMI. Do explore that link and find out more about the African Maths Initiative. It's well worth getting to know. It's a great project. And there you see...
IMSEC's about to start the latest MT2 online next week. So is it too late for anyone to sign up as a self-funded student?
There's a self-funded student. We could take 1 or 2 more. Yes, there'll be a large class there of 150. It's only secondary teachers, unfortunately. So thank you so much for participating. It's goodbye now. So thank you to you, everybody.
Thank you so much, Samuel, for joining us. And we'll see everybody next month. Thank you.
Thank you so much. I also see in the chat box. Thank you, Michael. Thank you, Letitia. Thank you, Anton. Thank you so much for today, and until next time.
This is a Global Teacher Empowerment Network video collaborating with AIMSEC and the Aiming High website. Our mission is to benefit children in disadvantaged communities all over the world by empowering the teachers who teach them mathematics.